All right, we're going to cover number 6 of 2019. This should have been a you-do problem, which means you should have already done this. If you haven't done it yet, pause this video, do it yourself, and then come back and grade it. But with that said, let's go ahead and get started. Here we're given f, g, and h are twice differentiable functions, where g of 2, h of 2 both equal 4, and they're equal to each other, obviously. The line y equals 4 plus 2/3 times x minus 2 is tangent to both of the graphs of g and h at x equals 2. In part A, it says find h prime of 2. Well, normally this is one of the easier problems to do, and it is easy here, but it's represented differently. If I want to know what h prime of 2 is, normally I'm given an h function or a table or a graph that I can observe. But here I didn't give anything of that nature. But what I notice is that it says in the prompt that this line is tangent to h when x equals 2. Well, if a line is tangent to a function at a point, that implies that its slope is equal to the derivative of that function at that point. And since it's tangent at x equals 2 and I want h prime of 2, that's an easy thing to think about. Since the line is tangent to h when x equals 2, that implies that the slope of the line is equal to h prime of 2. And so the slope of our line here is 2/3, which implies that h prime of 2 is 2/3. Points, you're only going to get 1 point for your answer here. So let's go ahead and look at part B now. It says let a be the function given by a of x equals 3x cubed times h of x. Write an expression for a prime, and then find a prime of 2. So here it's just testing our ability to take a derivative. So to take this derivative, I notice that there's a product here. So I need to take the derivative of the first thing and then times the second, plus the derivative of the second thing times the first. So the derivative of the first thing is 9x squared, and then multiply that by h of x. And then the derivative of the second thing is h prime of x, and then multiply that by 3x cubed. So that is my a prime function. And now to find a prime of 2, I just need to plug in 2 and then simplify from there. So when I go to simplify all that, I've got to figure out what h of 2 is, and that was given in the prompt. H of 2 is 4, so 4 can go there. And then h prime of 2, I already figured out in part A is 2/3, so I can plug that in there. From there, I just simplified a little bit all at once. 2 squared times 9 is 36. 2 cubed times 3 is 24. And then simplifying all of that, I end up with 160 as a final answer. And so, point values here, you're going to get 1 point for using the product rule correctly. So showing that you should have used the product rule and you did it right. 1 point for figuring out a prime of x, so 1 point for this final answer here. So chances are you got both of those points if you did the product rule correctly, but they're testing you to see if you know the product rule. And then 1 point for a prime of 2, so 1 point for your final answer here. One thing I want to note is that if you got this wrong, if you didn't get 160 because you got part A wrong, that might be okay for part B. So if you took your value from part A and plugged it into h prime of 2 and then simplified this correctly according to the value that you have here, you would still get that final answer point, because they're not going to ding you a point on part B for getting part A wrong. You already lost that point up here. So again, they read with you, which is kind of nice. So just make sure that whatever answers you get from prior steps, whether they're right or wrong, you got to have something there so that you can use it in future parts of that problem, because the AP readers will grade with you and read with you. All right, let's go on to part C. Part C says the function h satisfies this equation, h of x equals x squared minus 4 over 1 minus f of x cubed, for when x is not equal to 2. It is known that the limit as x approaches 2 of h of x can be evaluated using L'Hopital's rule. Use the limit as x approaches 2 of h of x to find f of 2 and f prime of 2. Now for me, when I first read this, and probably for you too, you probably read this and going, okay, L'Hopital's rule, I know L'Hopital's rule, but then when you started thinking about this, you had a hard time kind of putting it all together. Like, I knew that I had enough information to solve this, and I knew I could solve it, but I didn't know exactly where I was going to start and where I was going to end. So as I go through this, I'm going to show you how I did it. Looking back, I wouldn't have done it in the same order, but it still got me to the same result. And I just wanted you to see how my thought process worked so that you can maybe develop your own thought process. Again, it's not about doing it exactly the same way as everybody else every time. Sometimes it's about just starting with something and working through it until you get to something that leads you to something else. And so that can be a beneficial thought process. Don't just get stuck at the very beginning because there's a lot of big words here. So there's two thoughts that came to my mind immediately. The first thought was the idea that when I'm taking a limit, the first step is to try substitution. Since I'm trying to figure out the limit as x approaches 2 of h of x, I'm going to just substitute and see what happens. The second thought I thought was, since we can use L'Hopital's rule, then I'll take the derivative of the top and the derivative of the bottom and see where that leads. So the first thing I did was I said the limit as x approaches 2 of h of x is going to be equal to the limit as x approaches 2 of the function that it gave. Is going to be equal to the limit as x approaches 2 of the derivative of the top times the derivative of the bottom, because L'Hopital's rule applies. So that just made sense to me. So now to check this limit, I'm going to plug in 2 and figure out where that leads me. And so I end up with 2 times 2 over all of this. Now that's all fine, but I can't simplify that any further because I've got an f function in there and an f prime function. So then I started thinking through the idea of what it means for a function to be differentiable. It says that h is twice differentiable, which implies that h is differentiable, which then implies that h is continuous. You can't have a differentiable function without it being continuous. Well, if h is continuous, then that means the limit as h approaches, or x approaches 2 of h is going to equal h of 2. That's what it means to be continuous at a point. If that's the case, I know what h of 2 is. H of 2 is 4, which implies that I know that the limit as x approaches 2 of h of x is 4. And since this represents the limit, I can set that equal to 4. And so I end up with this equation. First of all, 2 times 2 is 4, so I just put 4 over all of this. That is my limit expression, equals 4, because I knew the limit is 4 because the function's continuous. Now from here, I notice that the top is 4, the numerator is 4 here, and on this side I don't really have a fraction, so I'm going to write that as a fraction. I'm going to just put it 4 over 1. Since the numerators are the same, that implies that the denominators are the same, so I can just set those two denominators equal to each other. If you didn't like that, you can just cross multiply and simplify from there. So now I have this equation that is true based on this limiting idea and based on this continuous idea, but I still have this equation with f of 2 in it and f prime of 2, so I can't figure out any values based on that because there's two unknown things. So it made me go back to the drawing board a little bit and go back to the idea of L'Hopital's rule. You see, I used L'Hopital's rule here when I took the derivative of the top over the derivative of the bottom. But L'Hopital's rule only works if, when you substitute into your original limit and you end up with an indeterminate form of 0 over 0 or infinity over infinity. And so that made me think, okay, well, if I'm taking the limit as x approaches 2 of this guy, if I go to substitute 2 into this, I notice that I end up with 2 squared minus 4 over 1 minus f of 2 cubed. Well, 2 squared minus 4 is just 0. And so that tells me when I went to substitute in this equation, I got a 0 on the top. Well, if L'Hopital's rule applies, That means I would have had an indeterminate form of 0 over 0 because the numerator was 0. That implies that the denominator must be 0. So that implies that 1 minus f of 2 cubed is 0. And then from there, since I only have one variable or one unknown, I can solve for that pretty easily. So I'm going to add f of 2 cubed to both sides, and then I take the cube root of that, and I end up with f of 2 equals 1. From there, I can take that value and plug that into this equation over here and solve for f prime of 2. So I end up with negative 3 times 1 squared times f prime of 2 equals 1. And then solving that, you end up with f prime of 2 equals negative 1/3. Now, like I said, I wouldn't have approached this problem in this order to start with. I would have probably started with the idea of checking for substitution first, because I know L'Hopital's rule works. When I plug in 2, I would have gotten this, and that would have implied that the denominator would have been 0. So I would have started with this line, and then that would have meant that f of 2 equals 1, and then I would have went over here just as far as a logical progression. As far as points go for this, you're going to get 1 point for figuring out that the limit as x approaches 2 is 4. So that's how I went about it here in this method. There might have been a different method to work through that logic, but as long as you came up with the limit as x approaches 2 of h of x is 4, you would have gotten that 1 point. You would have gotten 1 point for your answer on f of 2. You would have gotten 1 point for applying L'Hopital's rule. So basically this line up here, taking the limit as x approaches 2 of h of x is the same as the limit as x approaches 2 of the derivative of the top over the derivative of the bottom. And then you would have gotten 1 point for your answer on f prime of 2 is negative 1/3. Now one thing I want to note here is that your notation must be accurate. It must be right. It must have the idea that you're taking the limit along the way. You can't just say the limit as x approaches 2 of h of x is equal to this expression. You've got to have the limit out front, so be careful with your notation on that. All right, so for part D says it is known that g is less than or equal to h for the interval 1 is less than x is less than 3. Let k be a function satisfying g of x is less than or equal to k is less than or equal to h for 1 to 3. Is k continuous at x equals 2? And then justify your answer. So this part is actually dealing with a concept that we haven't really touched much on, and that's the squeeze theorem. So the first thing I want to say is that since g and h are differentiable, that implies that g and h are also continuous. And as a result of that, since g and h are continuous, we know that these statements are true, that the limit as x approaches 2 of a function is equal to the function's value at x equals 2. So the limit as x approaches 2 of g of x is going to equal g of 2 because the function's continuous, and because g of 2 equals 4, that implies the limit as x approaches 2 of g of x is 4. And the same logic goes for h. Since g of x is less than or equal to k of x is less than or equal to h of x, that implies, by the squeeze theorem, that the limit as x approaches 2 of k of x is equal to 4. And so you can see as g of x is approaching x equals 2, as x approaches 2, g of x is approaching 4. So we might have g of x that looks something like a curve up above. Sorry, it would be actually below. G of x is below. And then let me maybe sketch this a little bit. Let's say that this is g of x. And let's say that this is h of x. And let's say that this is when x equals 2 here. Oops. When x equals 2. And so we can see as we move along here, as x is approaching 2, g is approaching the value of 4. And then as x approaches 2, h is approaching the value 4. And because k is basically in between g and h, g is less than or equal to k is less than or equal to h, that implies that k must, oops, K must fit somewhere in between them because it's always in between them or equal to them. Oops, that is not a good picture of this. That is not either. Let's see if I can do this again. That's a little bit better, but let me adjust that. So you can see if the red line represents the K function, that its limit will also be 4 as x approaches 2 because it's in between there. So now we know the limit as x approaches 2 of k of x is 4. And since 4 is equal to g of 2, according to this statement here, and we know that that's less than or equal to k of 2, and we know that that is less than or equal to h of 2, and again, that's according to this statement given, and then h of 2 is 4, we can conclude that k of 2 will also be 4. Well, since the limit as x approaches 2 of k is 4, and k of 2 is 4, that implies that that is a continuous function at x equals 2. So that's kind of a wonky approach to talking about continuity at a point, but it's all derived from the squeeze theorem. In terms of points, you're going to get 1 point for your answer with your justification. That's it. It was a 1-point problem for all of that writing. Bummer. Anyways, go ahead and grade yourself on this and be honest with your grading. And once you have graded yourself, you're going to go ahead and move on to the next quiz. This is going to be the last problem in our Type 2 review of Calculus Basics. You're going to do question number 5 from 2018. It's a non-calculator problem, so set a timer for 12 minutes. Do it on your own, and then come back and watch the next video to grade yourself.